Professor Andrei Linde from Stanford University, USA. He will be speaking on the intro topic Universe or Multiverse. Professor Andrei Linde is the Emeritus Professor of Physics at Stanford University and one of the seminal architects of the modern cosmology. He is the originator of the chaotic inflation theory, a paradigm shifting framework that revolutionized our understanding of the Big Bang. Linde demonstrated that the exponential expansion of the early universe does not require fine-tuned initial conditions, but arises naturally from the dynamics of scalar fields. His work corrected the fatal flaws of the earlier models, firmly establishing inflation as the standard explanation for the uniformity and geometry of the observable cosmos. Linde's theoretical vision extends beyond a single universe to the concept of the eternal inflation, which posits that the cosmos is self-reproducing fractal multiverse. He showed that quantum fluctuations in the inflationary field continuously spawn new exponentially large parts of the universe, potentially with different physical laws. A recipient of the fundamental physics prize, the Kubler Prize, the Kirby Prize, and the Dirac Medal, Linde's contribution have fundamentally altered humanity's conception of our world, providing a mechanism that explains the origin of the large-scale structure of the universe. So with this, I would request Professor Andrew Linde to start his lecture.
Hello. Thank you very much for the introduction, and thank you very much for inviting me to give this talk. So I will start my talk with showing you the picture, which is right now became pretty standard in explaining the different stages of the evolution of the universe, starting from the Big Bang. So here is a Big Bang, and maybe simultaneously with the Big Bang, this was already a stage of inflation, which is exponentially rapid expansion of the universe at the very early stages of its evolution. Now, to understand why it is so, and also to explain the title of this talk about the universe and multiverse, I will first start with the citation of some quote from Albert Einstein, which was written not long before he passed away. He had written autobiographical notes in which he said that, and I will read here, I would like to state a theorem which at present cannot be based upon anything more than faith. That's amazing when somebody of Einstein's stature say that cannot be based on anything more than the faith in the simplicity, in intelligibility of nature. There are no arbitrary constants, etc. So what I will stop reading it. The main idea is that the universe is given to us in one copy, and we're trying to find out the reason for that, and we're trying to find out why the mass of the electron at far left from us a galaxy and a distant galaxies to the right of us, everywhere in the universe, mass of the electron is the same, charge, electric charge of the electron is the same, other coupling constants, other constants of nature, masses, everything is, well, do not change. It's everywhere the same. So maybe there is some real principle which explains why it must be so. And one of the main goals of inflationary cosmology, which I would like to discuss today, was to explain why indeed the universe is everywhere the same, and thus to realize at least some parts of the Einstein's dream, to explain why indeed in different parts of the universe you have the same laws of physics operating. And we have developed this theory, and after that we were up to a surprise that some constants of physics may be fundamental, and some constants of physics describe just what happens at our part of the universe and may be different in different parts of the universe. So I will start with why do we need inflation? And I can tell you the basic of the theory which we have developed during last 45 years. So this is the standard picture, uh, which is often used to explain how do we perceive expansion of the universe. The universe expands in all different directions from every single, and that is strange, from any single point in space. When you look, you live in one part of the universe or another part of the universe, you will see galaxies are always moving away from you, as if the whole space is expanding and they are moving away from any part of the universe. And then, if we try to describe this numerically, and maybe what do the following: when the universe expands, what's if we run movie back in time? Here, the universe originally was smaller, smaller, smaller. So when we run movie back in time, we see the time where the galaxies were very close to each other. Actually, they were smashed each other. There were only elementary particles flying. The universe was very dense, and there was some moment which is called Planckian density. That we cannot even go beyond this Planckian density using present state of physics. At this Planckian density, which happens also at the time 10 to the minus 43 seconds from, and that is from if there was a big bang. So we come very close to something, and then movie stopped working. We do not know what was there. So this was a big bang. And now, if we, using this standard theory of the Big Bang, calculate which part of the universe I was able to see, or whatever, imagine somebody looking at that time at the universe, we will see that this person will be able to see only at a distance 10 to the minus 33 centimeters, because the universe is so young and the light traveled only at this distance. And the size of our part of the universe, if we play it back, at that time was not so small. It was about 1 centimeter or so. So then one can see only tiny, 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 tiny fraction of the universe at this Planckian moment. And this tiny part will contain only one elementary particles, or maybe 10 elementary particles. But at the moment we have 10 to the approximately 10 to the 90 degree of elementary particles. So if I would like to do something with the universe, making it homogeneous, large, whatever, I would be unable to do it, because I, or whoever tries to do it, can affect by anything that he does only 10 to the minus 90 of all particles in the universe. So that's the problem with the standard Big Bang. It's very, very difficult to imagine why this universe emerged that way, why it was so large, why it contained from the very beginning so many particles, why different properties of the universe in different parts of it were the same. And that is why I will skip it. And that is why inflationary universe theory came as a possible solution of it. So the standard Big Bang cosmology can be illustrated by this picture. Suppose you have a box with, for example, 1,000 protons. Universe expands and the box grows in size, but it still contains 1,000 protons. Nothing more, nothing else. The total number of particles in the standard Big Bang cosmology practically did not change. Maybe changed twice or three times during the whole evolution of the universe. But you get right now the same particles that were before. And that is why it was very difficult to explain the origin of the universe. And there are many different problems about this Big Bang theory. What was before the Big Bang? Why the universe is so uniform? Why it is not exactly uniform? Because we need some non-uniformities to create galaxies. Why it is isotropic, means the same in all directions. Why all of its parts started expanding simultaneously. why it is practically flat, not closed, not open, but with a very large accuracy. It's flat, which in cosmological language means some parameter omega equal 1. Well, so all of these questions. And for the first one, we still do not know the full answer, but we are coming closer and we have some ideas based on quantum cosmology. And all other questions would have some possible answer with the contents of inflationary cosmology. So, the basic idea of inflation. Now, do not take the box with 1000 protons. Instead, take the box with a heavy vacuum. And this sounds very strange. What does it mean, heavy vacuum? Well, just not far long ago, approximately 27 years ago, we found that empty space in the universe is not exactly empty. It has some non-zero vacuum energy called cosmological constant. So vacuum may have energy, and in fact, this is a part of the modern theory of elementary particle physics. It may have energy first stored in itself, and then depending on some fields which exist in the universe. The most famous one is Higgs field, and there is a Higgs effect, which is the basis of electroweak theory. So you may have energy stored in the vacuum. And when you think about vacuum, this is something which is characterized by energy density of the universe. So when the universe expands, energy density of empty space remains the same. Nothing changes, it's the same empty. So the energy density remains the same, but the total energy is proportional to volume. And therefore, if this picture makes any sense, then interestingly, the total energy of the universe will continue growing and growing and growing just by, well, letting the universe with a heavy vacuum expand. So this look something wrong. It couldn't be so. But the situation is rather tricky, and it actually happens quite consistent with known laws of elementary particle physics. Energy for the whole universe, including gravitational energy, is conserved, but energy of matter is not. You have a balance between gravitational energy and energy of matter. And if you have this configuration, which I've shown you, the total energy of matter can grow and it will be proportional to the total volume. So the larger is the universe, the more energy it has, the matter energy of the universe. Basic idea can be illustrated by describing this vacuum expanding in the expanding universe, and that's the first simplest equation, which is Hubble equation, showing that the speed of expansion is proportional to here I have a typo. The speed of expansion is proportional not to v, not to potential energy squared. It is proportional to energy. So I will need to erase this factor 2 there. It has a solution which describes the universe growing exponentially. It just, you solve equations in general theory of relativity. You have this answer. There is nothing special about it. And then total energy of the universe is growing exponentially, because if size of the universe grows exponentially, then the total energy is volume, grows like volume, so it goes three times faster. And that was the basic idea of inflationary theory proposed by Alan Guth in 1980. And that was great idea, absolutely. But then if something looks too good to be true, that sometimes it is too good to be true. If the universe is empty, how can anyone know that it expands? The universe with a constant vacuum energy is described in general theory of relativity as de Sitter space. And for de Sitter space, it is known some paradoxical thing that in one coordinate system it expands, in another coordinate system it collapses, and another coordinate system is static, because it's vacuum and there is no way in vacuum to define what is expansion. So there is no preferable coordinate system. And as a result of that, when this vacuum starts decaying to produce normal matter, then this decay happens very inhomogeneously, and the universe becomes very, very bad, very inhomogeneous. So after about a year of investigation, Guth, as well as Hawking with their collaborators, concluded that the theory cannot be improved and does not work as it is. But fortunately, it was possible to break some of the assumptions of the original theory. And instead of vacuum, which stays with constant vacuum energy, one should consider scalar field, which slowly changes in time. And this slow change is very important ingredient of the theory. So if we do it, it's possible to avoid this objection which I just gave you. And the simplest scenario, which was already mentioned in the introduction, is the so-called theory of chaotic inflation. That's the simplest version of it. You have a theory where a scalar field, which uh, exists everywhere in the universe, you would consider it in a tiny speck of space in the universe and assume that it is more or less homogeneous and slowly moving. The first line is Lagrangian describing this universe. So if you study the theory, the first term is R, is gravity, the second term is kinetic and gradient energy of scalar field, and the third one is potential energy. So if you let the scalar field evolve, it does not want to have any non-zero value. Its potential energy is similar to this curve which is written here in this picture. And the scalar field looks like a ball here. So if you start with scalar field having very large magnitude, it wants to go slowly down. But it goes down slowly because of some magic of equations here. This second equation describes the motion of the scalar field, and it contains this term 3h phi dot, which in normal mechanics called friction term. If you study harmonic oscillator, its equation will be exactly like that. Phi 2 dots is equal to minus m squared phi. That's equation for harmonic oscillator. The second term is friction term. And this friction term tells you that if Hubble constant, which stays here like a friction coefficient, if Hubble constant large, then the scalar field moves down very, very slowly, and therefore during a long time, scalar field stays approximately the same height. If it stays at approximately the same height, then the analysis which we made before using these equations is approximately valid. Energy of a scalar field is approximately constant, then expansion of the universe is approximately exponential. And that was the basic idea. And you solve these equations exactly already for the scalar field phi, and use this analogy with harmonic oscillator, analyze it, but you solve this equation exactly. And what you find is that the universe expands approximately exponentially and become very large very quickly. So you may start with the whole universe occupying only the having size 10 to the minus 33 centimeter, which is Planckian length. You cannot go smaller than that because you will be unable to describe it in terms of normal physics. And at that time, energy may be smaller than a mass smaller than a milligram, and then you wait very small time, approximately 10 to the minus 30 seconds, and the universe becomes as big in any units of length. And if you have here any mountains, any inhomogeneities on the universe, then they are stretched, the universe becomes uniform, and all the problems which bothered us before, they disappear, they are solved. So, where the particles? If you have no particles there, only scalar field, and then it becomes huge, these elementary particles were created by the decay of the scalar field, and it happens gradually in all different parts of the universe, and there is no collisions of the walls of the bubble, which was a property of a theory of Alan Guth. So the universe becomes almost uniform. But almost uniform is not a good thing because you need to have not just a spherically symmetric ball which is totally uniform, you need to have some inhomogeneities which give rise to galaxies. And here quantum mechanics helps. And that was the following. In vacuum, even right now, we're surrounded by quantum fluctuations. And in an expanding universe, these quantum fluctuations, they grow in their wavelengths. And then universe continue expanding and they grow. And eventually they overlap with each other and form this slightly inhomogeneous background. The theory of this was developed for the first time by Mukhanov and Chibisov in Russia, and I was at that time also working there in the nearby office, and I told them, well, but this does not make any sense because you are saying that galaxies have been formed by quantum fluctuations. This cannot be right. And then I tried to understand, and yes, that was brilliant idea. And that actually, right now, this is the only mechanism which accepted by everybody the theory of formation of large-scale structure of the universe created by quantum fluctuations. So this will be important part of understanding of what this multiverse is about. Quantum fluctuations can form large-scale structure of our universe. When I am talking about inflation, you may say, oh, but who knows? It's like science fiction. Nobody was there to observe the universe. How we really know that this theory is accurate? Well, first of all, this is at the moment the only theory that I know which was demonstrably. People came and checked and checked and checked that the equations are right, the derivations are correct. The only theory which we know that can explain why the universe is large, why it is isotropic, why it is uniform. It also predicts that the perturbations produced by inflation are of a special kind, adiabatic, and that's exactly what was found experimentally. They also show that perturbations have some special peaks in the spectrum, and the peaks of the spectrum were observed. They show that the two different types of perturbations which exist there, they must have some anti-correlations, and that was also something observed. Then inflationary perturbations were predicted to have practically flat spectrum, do not the spectrum which does not depend on the logarithm of distance, and that was also confirmed, and many other things which I mentioned here, something about non-Gaussianity. So about 10 different pieces of evidence in favor of inflationary cosmology. So let's assume that this is the theory which describes our world. In particular, this was the picture obtained by Planck satellite about 10 years ago, which shows perturbations, tiny perturbations of temperature of sky, which we look around right now. It's really, really tiny at the level of like 1 divided by 10,000 of temperature of the microwave background radiation. It was possible to find all of these small things. And this is essentially a photograph, a photographic image on the scale of all observable part of the universe of results of quantum fluctuations at the birth of the universe. So it's really amazing. And there are some ways of making it numerical. I do not have any possibility to go into details to specify, to quantify these predictions and how the observation check it. For example, some spectrum must have some peaks, and that's exactly what Planck satellite have found. And then it was studied in greater details for different types of perturbations by subsequent experiment, ACT and SPT, and they all confirm the prediction of basic inflationary theories. And it's possible to test it even better if we find out not only this simplest type of quantum fluctuations which was predicted, but also gravitational waves. But spectrum of gravitational amplitude of gravitational waves produced by inflation is expected right now to be much smaller than these simple perturbations studied by Mukhanov and others. So far these are not found, but many people are working on them. It's possible that we will never find it because the amplitude in many theories is so small that whatever we try, we'll never find it. But if we find it, it will be additional 11th evidence in favor of inflationary theory. And that is from a recent paper summarizing experimental status of investigation of inflation in the end of 2025. So just latest paper. Again, if there are any specific questions about details of that, I would be happy to return to it. Right now, it was only to show that people are really doing science about this theory, which originally looked like science fiction, and so far looks so good. And I probably will not discuss the details of the theory. So I will mention you only this. I gave an example of the theory with the simplest potential, m squared phi squared. The simplest, like a harmonic oscillator. But this simplest theory predicts the spectrum of perturbations, which was already ruled out experimentally because it would predicted to produce too large amplitude of gravitational waves. However, it is sufficient to modify this potential just slightly, add two different terms of polynomial for the potential, make this potential looking like it is right now, and everything will fit present experimental data. Okay, so that was a basis of the theory. Now we are going to something more interesting. Well, this was uh, incredibly interesting when we were discovering all of this, but this was the story of 45 years ago. Now we live with consequences. And the consequence is the following: uniformity of our universe is explained by inflation. So exponential stretching of the universe makes all parts of the universe looking alike because they originated from the same place. But now, and that will be the modern part, that on the larger scale, the universe can be and probably should be 100% non-uniform. And that will be this uh, discussion of the multiverse. Here comes the general idea of why this could be so. Remember, we start with this small red ball and then expanding, and when it expands, the whole universe becomes red, which means that if one or part of the universe had some specific properties, by red, I mean vacuum state of a specific type, then the universe exponentially expands, and this vacuum state expands on the whole universe. When you have laws of physics of a given type operating this red ball, they expand and the universe becomes red everywhere. Everything is similar to what was in the beginning at the expansion of this red ball. But if I start with a football, you have a universe, part of it was red, part of it was white, part of it was blue. And then it blown up by exponential expansion of the universe. And we live, for example, in the blue domain, the blue part of the universe. And in the blue part of the universe, we will look around at the huge distance, we will see only blue. And in the white universe, we'll see only white. By this blue and white, actually, what I mean is that our universe may have some different realizations of laws of physics in different parts, and I will explain it later. Okay, and if we look around, we will see surrounded by a part of the universe of certain properties. The people who were born, and whoever was there, who was born in a yellow universe, they will see the universe of this type of properties, and nobody would suspect that somewhere else the properties of the universe would be different because all our experimental data would be about blue universe if we live there, or about red universe for those who live in this red universe. So then, how do we know that our universe does not have these red and blue and green different areas with different properties? And there are two um, attitudes to this question. One of them is a pessimist, and a pessimist says that if the multiverse which is so large and it contains different parts with different properties, is so huge that we never see other parts, then it is impossible to prove that we live in the multiverse. An optimist says, if, and look, optimist practically repeats what pessimist said. If each part of the universe is huge, we will never see other parts, so it's impossible to disprove that we live in the multiverse. And the Einstein said, I would rather be an optimist and a fool than a pessimist and right. So the whole idea is that the basic theory is that you have a multiplicity of different things. And how can you prove that our universe is everywhere the same? And previously, we had an idea about the universe. Then we have a telescope. You look at the telescope and you see, and you look at the whole universe. But in inflationary universe, the size of the universe is billions and billions and billions of times larger than the small parts which we can observe in the telescope. So how do we know what is in the other parts of the universe? And what else happens is that even if we start with the universe of one particular type, quantum fluctuations may divide it into pieces with different types of, well, effectively universes. Because for each of us who live in this huge red area or huge blue area, this would look like everything, but we will just be able to see only a small part of it. I think that I better skip into some philosophical discussions here because I have only 15 minutes, approximately 15 minutes, maybe 20, to the moment when I should finish. I will go directly to some realizations. So this is a technical example. This is the theory which was known to physicists long time ago. In 82, Steven Weinberg, famous physicist who invented standard one model of elementary particle physics, he described something which is called supersymmetric SU5 model. This model has potential energy which have three different minima. In one of them, symmetry, SU5 symmetry between elementary particles is broken. In other, you have a symmetry describing elementary particle theory of a different type, SU4 cross U1. And another one, we have symmetry which just describe the science which we observe around us. Okay? And he asked the question, how can we come? Why we are not in the most symmetric minimum? Why we are in this SU3 cross U2 cross U1, which is necessary for having strong, this is SU3, weak and electromagnetic interactions, which is these two groups, SU2 and U1. And he studied thermal beginning hot Big Bang universe and found that in the beginning only SU5 minimum existed. So how we will be able to jump to this SU3 minimum if in the beginning it was only SU5 and then gradually this one appears, but what would force us to come from SU5 to the part of the universe of our type? And I found the possible answer. During inflation, these quantum fluctuations bring us to all of these minima of the potential SU5, SU4, SU3, and therefore in our huge multiverse, you will have parts of the universe where this symmetry SU5 is unbroken, and there is no difference between leptons and baryons in this universe, and we cannot live there. In some parts of the universe, you have physics of this type SU4, and in some of parts of the universe, you have this SU3 cross U2 cross U1, and we can live there. So no surprise that we live in a part of the universe where we can live. We cannot live in the red, we cannot live in the dark blue, we can live in these green ones. The only problem is how you create them. And so we make computer simulations of quantum fluctuations in this theory. And you start with the universe, which was in the beginning red, and then quantum fluctuations change it. by what I mean by red, etc. Remember, I have shown you minima. One minima we painted red. So if you are in SU5, you show the universe red color. If you are in this minimum, blue. If you are green, then this is what we want. And you start quantum fluctuations, you run, and you see how you start with red, and then quantum fluctuations divide the universe in different parts. Universe at that time continue growing and growing exponentially, and it continued this process of division into different regions. Scalar field jumps from red minimum to blue minimum to red minimum, back to green minimum, and then gradually this kind of stabilizes, process ends, the field stops jumping, it lays down an expanding universe in one of the minima, and we live in one of these minima. And this is the end story. You have some parts of the universe where it is blue, and we cannot live there. Some parts of the universe where it is red, and we cannot live there. And some parts where green, and we can live there. That's the main idea of the universe, multiverse. This particular version of the universe is just very similar to what we have on Earth right now. You have on Earth where you have different countries. You have China, you have Russia, you have United States, you have India, and each of these countries have their laws operating on each of them. So you have a universe which is expected to be much larger than people thought before the is, and it is divided into different countries, if you wish. One country with its blue law of physics, SU4 cross U1, another with red, SU5, and another is green, and this is our physics. And we can live only in the parts where we can live. So we learned an interesting lesson. Okay, uh, Alan Guth in 81 said, it is said that there is no such thing as a free lunch, but the universe is the ultimate free lunch. And that was something which he said a long, long time ago to illustrate that what happens. You have practically nothing in the beginning, and then you have everything. How is that? It's free universe with all of these 10 to the 90 particles and more produced from practically nothing. And then next step was when I said, now the universe, that the universe is not just a free lunch, it's eternal feast where all possible type of dishes, green, blue, orange, whatever types of whatever is possible are served. We have different vacuum states in different parts of the universe. But at that time, it looks like, well, science fiction. I've said it, I've written it in some proceedings. Nobody cared because it's a bit too abstract to think about things like that. This whole thing is science fiction. Gradually, people start understanding that this is not really a science fiction. But if it would work, this would be magic, because we would be able to justify the anthropic principle, explaining that we live in those parts of the multiverse where we can live. Now, what changed lately, starting from 2003, in 2003, at Stanford, together with Kachero, Kalash, Trivedi, which was well, a very talented physicist from India, and we developed something which is called KKLT mechanism in the name of the authors, which explains how to stabilize vacuum in string theory. It is extremely complicated theory. I was there mostly like a cosmology consultant. It was studying tunneling from one vacuum to another. But what we have studied there, if this string theory of this type is correct, and people are still debating it, there is no statement that this is the truth, absolutely. But this is come as close to truth as we can check at the moment, at least some possible realization of it. So what we have found, and other people found the number of different vacuum string theory. We have found a way to stabilize vacuum in string theory. And vacuum in string theory depends on, in string theory, you start with 10 dimensions, but 6 of them are compactified, and four remains, and three of them are space and one time. So why six dimensions are compactified? And could they be compactified differently? What if only two of them are compactified? How many different options, different possibilities to do so? And what fields live in these different dimensions depending on different types of compactifications? And then when they estimate, they found 10 to the degree 500. That's not 1 billion, that's not 100 billion, that's not 100 billion, that's not even a Google. This is much greater number. And then they start calculating, maybe we made some mistaken estimates, and then they start talking about not, no, maybe it's not 10 to the degree 500, maybe it's 10 to the degree 1500. So then now some people say, no, it all is impossible and everything is different. Well, we do not know really, but string theory is the best toy model of how the universe may look. So it is a very serious thing. And so many string theorists took these results very seriously, and they start then thinking, so what does it mean? If our universe may have not just three colors, which I've shown you, universe is green and red and blue, three different types of vacuum, and each vacuum gives you different laws of particle physics living in this vacuum. So maybe not three colors, but it's 10 to the 500 different colors, much more than any of our computers can produce. And then we start checking what is the probability for us to live in the green universe as compared to others. And here I cannot stop. There cannot describe all of this with discussion of probabilities. If you have some questions about it, I will answer. But the basic idea is that, and this is an example of vacuum energy. People did not know why vacuum energy, which was discovered in 1998 by supernova observations, why it is so extraordinarily small. People thought that vacuum energy is just zero because it's vacuum. They found experimentally that this is not zero but extremely small. However, if vacuum energy corresponding to the minima of these potentials, if vacuum energy would be much larger than this tiny volume, then the universe right now would expand too fast and the galaxies would be torn apart. If it would be small but negative, then the universe would collapse and we also would be unable to live. And only when the vacuum energy is exactly in the range which was experimentally discovered, people like us can exist in the universe. So you have strange coincidence. If you think that the universe consists of 10 to the degree 500 different types, then there are many, many vacua where we can live, and we do not care about others where we cannot. Another example, why we live in the universe with three dimensions. Well, I spent some like 3 months in the Leiden University in Netherlands, and this university, at each floor, in each corner, you see portraits of Ehrenfest, and here is in the middle here, surrounded by Einstein and Lorentz and others. So nobody there knew that in 1917, Ehrenfest produced an explanation why we live in three-dimensional universe. Why indeed? Because, of course, why would we have any other choice? In a normal theory, yeah, well, we live in three-dimensional space. So you open any textbook on physics, you live in three-dimensional space. What's the question? But in string theory, you live in 10-dimensional space. And then after compactification, some part of it may be compactified, and you will see that it is two-dimensional, and some parts of in some parts the universe is five-dimensional. So why we are living in three-dimensional universe? So he gave the solution of this question even before any string theory was invented. He said that if we live in the universe with more than three spatial dimensions, then planetary systems would be unstable and atomic systems would be unstable. If we would live in the universe with two dimensions, space dimensions, or one, then there are no gravity forces at all between different bodies. This is a surprising fact which can be understood only in contents of general theory of relativity. So now we know that if we would have a chance to have universe consisting of different parts with different dimensionality, now we understand that we live in three-dimensional universe. We require planetary system for our type of life. But somebody else who does not need planetary systems, they may live in some other parts of the universe, in six-dimensional, 10-dimensional universe without any compactification. But there is a, it's not that we are creating the universe by our desire. It's we're establishing relation between the universe and the our part of the universe. It's proper ourself and the properties of the universe where we can live. Like dolphins can live in water, and humans can live only in solid land, water only temporarily. So this is just a relation between us and the properties of our part of the universe. No metaphysics here. Can we test the multiverse theory? And that is an important philosophical issue, because I already mentioned to you that different parts of the multiverse may be so enormously large that you cannot ever see these other parts of the universe. So you may often hear somebody say that, yeah, but the theory of the multiverse, you cannot get any experimental confirmation of this theory. Well, in order to analyze this, I will use an authority which was not really of a scientist, but of a great, detective. Sherlock Holmes, of course, it was the person who suggested some basic principle, which actually a very important part of the way how we operate, even in science. He said that when you have eliminated impossible, whatever remains, however improbable, must be the truth. So, what did we eliminate? What is the truth? For about 100 years, we were trying to find out why the vacuum energy is so small, and maybe why it is exactly zero. And now it's so immensely small, and we so far, 27 years after the discovery of the small cosmological constant, we have no other way of explaining why it is so small except for using these anthropic considerations. Consider neutron and proton. The mass of the proton and the mass of the neutron differ by less than 1%. Why they are so similar, the different particles, why they are so similar? It's just coincidence. Well, if the proton would be 1% heavier, then all protons would decay into neutrons. And what you will have are only neutron stars, not single person. If neutron would be 1% heavier than the proton, then neutrons would decay to the protons. There would be no different atoms except for atom of hydrogen. Also, we cannot live there. So we say, oh, anthropic principle explains why neutron and proton are so similar to each other. How about the electron? Electron has mass 2000 times smaller than the mass of the proton and neutron. Why it is so small? Oh, let's think about the part of the universe where electron is, say, 10 times heavier or 10 times lighter. Physics would be different there. We would be unable to live there. How about the charge of the electron? Change it significantly. We also cannot live there. But all of this looks like cheap philosophy. It is like, uh, something unhealthy with this. Anthropic principle, physicists hated it until you have a physical realization of why this anthropic principle may make sense. And for that, we really need a possibility to live in the universe where electrons have different mass and the proton has different mass and the dimension of space have different dimensions than three. Then suddenly you have a theory which explains all of these puzzles all of these dramatic coincidences uh, which exist in physics and going well beyond the physics. For that, we need a multiverse. So the multiverse right now is the only uh, framework which allows you to answer to all of these experimental questions. Experimental question, why the cosmological constant is so small. Experimental question, why proton is so similar in mass to neutron, and why electron is so light, and what is the value of its charge. These experimental questions are now now we have a way to examine it and to possibly give an answer in this context. And so far, we do not have any other answer. And then using this principle, when you have eliminated the impossible explanation, so many years we're trying to give an explanation to this experimental fact. And now we have explanation of this experimental fact. And it's only the theory of multiverse gives this explanation. Unfortunately, I am afraid that this is a time for me to stop, and I would be able to go a little bit longer, maybe just 3 minutes. Can you give me 3 minutes?
Yes, sir, sure. Yes.
Okay. So, just to illustrate the strange way of thinking about things which appears right now. Long time ago, Albert Einstein said, the most incomprehensible thing about the universe is that it is comprehensible. How is that? Our universe was well created in the way we can understand it. We have science, we have some, well, mathematics works perfectly well there. So this is a mystery. Then mathematician Eugen Wigner said, the unreasonable efficiency of mathematics in science is a given we never understand nor deserve. So how is that? The most famous physicist does not understand why physics work. The most famous mathematician does not understand why mathematics work. Then famous Russian mathematician living later in the United States, Gelfand, says, there is only one thing which is more unreasonable than unreasonable efficiency of mathematics and physics, and that it is unreasonable ineffectiveness of mathematics and biology. So all of these people were saying something like that. Why? Why is that? Why we're so lucky that we have a theory which can explain our universe? Why the theory? Why it works? And the reason why Einstein was puzzled and Wigner also by efficiency is that if the universe is everywhere the same, no choice, then the fact that it obeys so many different laws that we can discover, remember, and use can be considered as an undeserved gift of God to physicists and mathematicians. Okay, so maybe this is how it worked. But can we have alternative explanation? And the alternative explanation is that in the inflationary multiverse, which you may also say, okay, but this was also created by God. But I'm just saying you that in inflationary multiverse, the laws of mathematics and physics are efficient only if they allow us to make reliable predictions. That means efficient, okay? And this reliability of predictions is necessary for our survival, because this is how the game of fitness appear. We can predict what happened with us. That's why we can well win in the game of evolution. But this means that we can live only in parts of the universe which allows efficient physics and mathematics, because this is necessary for these calculations to be made and the results of it to be remembered. So we live only in the parts of the universe where mathematics and physics are efficient. That solves the problem which bothered Einstein and Wigner. And this looks like that. This is now, and this is my last slide. This is the way how we can illustrate. This is kind of a sketch, but nevertheless, this is a multiverse. You start with the universe with some type of physics operating in them, and then it starts producing different parts of the universe, and they produce new different parts of the universe, and they are so huge that people living there, they will think, looking at this neck containing, which is at the moment, at the place where this bubble emerged, you will see this is the Big Bang, we will say. But this is a Big Bang, this is very big something, but this is not a Big Bang. And where's the Big Bang? Or go back. Okay, so how far go back do I need to go to find the real bang? So this is now the fractal universe, and we can live only in the parts where physics is compatible with our existence. And physicists and mathematicians can live only in the parts of the universe where mathematics is efficient and the universe is comprehensible. And at that, I finish my talk. Thank you very much.
Thank you. Thank you very much, Professor. We are deeply grateful for your profound exploration of the cosmos, which provided our audience with a rigorous analytical framework for understanding the structural complexities of the multiverse. Now, moving forward. Yes, this is a question from Dr. Bharat Pandey from the Government PG College Raniket from India. He's asking, Sir, I want to ask if galaxies are ultimately the result of quantum fluctuations, does that mean the universe at its largest scale is rooted in quantum uncertainty? And if so, how does this uncertainty give rise to the precise patterns and uniformity we observe today?
Okay. So here are two tricks, one after another. First, you have global expansion of the universe. And imagine that you have Earth, and the radius of the Earth grows exponentially. Then there will be no alpinism in Himalaya because Himalaya will be stretched, it will be horizontal. And so inflation removes previously existing inhomogeneities. Quantum fluctuations allow to create new inhomogeneities on the top of already homogeneous universe produced by inflation. So if these quantum fluctuations are not very large, then they produce small perturbations which later grow and they produce locally galaxies. In one place, one galaxy, another place, one galaxy. This is a result of amplification of quantum fluctuations. Okay, in parts of the universe where these quantum fluctuations were large, then they can bring you from red universe to blue universe. That does not happen at a small scale. This requires very large fluctuations, which are very rare. So we live in a part of the universe where everything of the same type, and the maximal result of that are these local fluctuations of the galaxy type, which we observe right now.
Okay, thank you. Thank you, sir. So let's move to the next question. This is the question by Mr. Srinjay Paul from University of Kalyani. So in inflationary multiverse models, what defines probabilities if there is no preferred observer? How do we interpret probabilities across different possible universes?
Well, since you asking a question, you yourself is a preferred observer. When the moment when you ask a question, you ask a question. Okay, let me look at my hands. Oh, they are made from some materials. Let me study what is a part of these materials. Or they have electrons there and protons there, etc. Or so you learn quite a lot of information before you ask a question about cosmology. So then, your questions about whether you live in a red universe or blue universe are already conditioned on some answers to some questions related to you. At this moment, you have created already by your previous knowledge, by the previous study, you have created a base of knowledge which make some questions specified for your part of the universe in which you can live. It would be excellent if we would have a possibility to predict also that you must live the greatest probability of this type of the universe. This is so far not a solved problem, and we do not even know whether this problem uh, whether it can be solved because somehow we physicists are roots about in the idea, rooted in the idea of objective reality and everything, and things like consciousness usually do not matter for them, and many other things which are kind of more interesting to the institute where I'm giving a talk right now. Um, but yes, that the questions which you asked are uh, already specify that you live not in the green universe, sorry, not in the red universe where you cannot live, but the green universe. Then you already put yourself firmly in the green universe with these properties of elementary particles, particle physics, actively working there.
Okay, thank you. Thank you so much, sir. So let's move to the next question. This is the question by Professor Tejendra Singh from the Tata Institute of Fundamental Research. So he's asking that in the
Yeah.
enormous string theory landscape produced by different compactifications, have we derived one which reproduces our observed universe? Say one that has the low energy fine structure constant is 1 by 137. There are 3 fermion generations, and
Yeah.
the muon is 206 times heavier than the electron.
Yeah. Okay. So the answer to this question will be a bit disappointing. On the other hand, it will explain the way people think about it right now. Disappointing in the sense that string theory is immensely complicated. When we start working on this compactification and other things, I was surrounded by three wonderful string theorists who were working in this area. Uh, there are many outstanding physicists and mathematicians working on this, but string theory is just immensely uh, complicated. We even do not know, honestly, whether this KKLT mechanism or some other mechanism of compactification of the universe, whether they are really achievable or not, simply because of the complexities. So what we did under certain assumptions, we have this construction, seem to be, at least at the first glance, consistent. What will be the consequences? So other people come and have slightly different version of string theory and have completely different consequences. And the only fact that remains that whatever type of string theory they study, usually, and I mean, if everything works, okay, then the total number of types is combinatorially large. It actually goes back many years back in time to when I visited academician Andrei Sakharov in his exile in Gorky, and Sakharov was creator of Russian atomic bomb, one of the main leaders there. But he was also outstanding physicist, and he was interested why cosmological constant is so small. And he said, if the, and this was before string theory, or at the moment when it started just generating, people start talking about many compactifications. And he say, okay, consider the universe with sufficiently large dimensionality, then combinatorial possibility of topologies which emerge as a result of compactification of sufficiently multidimensional universe is exponentially large. And that explains the number of different possibilities that you study. So if you have 10 to the degree 1000 of different laws of physics, then it is not so surprising if one of them gives you the muon mass exactly as it is, and another gives you top quark mass exactly as it is, and the number of dimensions exactly, because we have right now the total number of options so large that it does not fit your mind. And that is my only way of answering this question.
Okay, thank you. Thank you so much, Professor. Moving to the next question. This is also from Dr. Bharat Pandey from Government PG College, Raniket. So he's asking that Newton gave us universal laws and Einstein refined them for our universe. But in the idea of the multiverse, are these laws truly universal or just local to our universe? Could these exist universes where even gravity or space-time behaves completely differently?
Okay, the answer is this. Newton considered three-dimensional flat space without any gravitational waves and curvature. We already know that this is not completely right. Einstein make a next step and say that our universe can be curved, and in some limits you reproduce the laws of gravity by Newton, but it was still three space dimensions and one time. String theory came and said that we live in a space with 10 dimensions, so 9 dimensions of space, 1 dimension of time, but why we don't feel that this is the case? So we have these different types of compactifications. And once we have different types of compactifications, there could be, as I already mentioned, the universe which is two-dimensional. And in two-dimensional universe, there is no gravitational attraction between far removed bodies. So yes, indeed, that is the main well subject of the talk. That if our theory is general enough, and string theory is just an attempt of a theoretical description, which may be the best which we can do right now. Maybe it's totally the best. Maybe it's just the same beginning like Newton theory was for Einstein theory. But what it tells you that the total number of possibilities in this theory can be, no guarantee, but can be exponentially large. And then, therefore, realization of different laws of physics in different parts of the universe may be different. It's, if you wish, there may be a fundamental law of physics and like phases. Like water can be liquid and solid and gas. It's the same chemistry, the same H2O. But when your ship goes in water and the captain thinks that only water exists, then no surprise that Titanic crashed into iceberg. Okay, so we just must be prepared.
So this is by Mr. Nikhil. If the effective laws of physics arise from the compactification of extra dimensions in string theory, can we meaningfully think of this compactification data as the genetic code of the universe, analogous to the DNA encoding the biological traits?
Yes, and actually, the first time I've heard this analogy from Leonard Susskind, who have written a book containing this description. Indeed, if you have some uh, original genetic code of the universe. You start with the universe having like electroweak interaction and strong interaction and gravity, and then inflation happen in this kind of universe. Then in some parts of the universe, quantum fluctuations make this universe to bifurcate. You have mutation in a genetic code, and you produce slightly different type of laws of physics, and then there continue mutations continue. uh, so this analogy is very fruitful. On the other hand, the complexity of the situation and the possibilities which we are encountering right now, they are must more diverse than the simple pic. I'm calling it simple. The simple picture when the universe just grows like a tree and produce you different parts of different colors. This simple possibility is not the only one possible. And I mentioned it in some of the slides, and I didn't even discuss it, that if you believe in quantum cosmology, then any solution, any possibility, um, which not even the possibility which cannot be created by mutation, because mutation of an elephant produces an ill elephant, but maybe it will still want to produce something similar to elephant and not produce a bug. Okay, so these tree may produce quite a lot, but these basic trees may be different. So in quantum wave function of the universe may uh, contain information about all of these possibilities, even more than what can be produced by bifurcation. And then we come to something even more basic. So, what does it mean about these laws of physics and where they have been written if there was no blackboards to write them and people to remember? So, well, the very important questions where the issue of what consciousness is, what the universe is, in some more fundamental level come to game.
Okay, thank you. Thank you, Professor. So we'll take one more question. This is by Miss Samisha Shaikh from Edify School, grade 12. Professor Linde, regarding eternal inflation, we often discuss the birth of bubble universes. Is there a physical mechanism within the multiverse framework that allows for collapsing bubbles or regions of local contraction to coexist alongside the global inflationary background?
Yeah. Okay. So the answer is the following. Suppose you have piece of cheese with bubbles in it. It's like Swiss cheese. Okay. So this is a Swiss cheese universe, and bubbles start growing inside the Swiss cheese. But the piece of Swiss cheese expands faster than bubble grow. Then this bubble will never cover the whole universe, and the other bubbles also. So that's the rather strange situation, which is possible because of general theory of relativity, because of this exponential expansion. That if something happens inside an exponentially expanding universe under certain conditions, not always, but under certain conditions, this uh, tunneling to unstable regions. You can go from exponentially expanding state, then locally you can tunnel to anti-de Sitter space, which immediately collapses and disappears. But this wall of anti-de Sitter, of something collapsing, expands with the speed equal to the speed of light. But the exponentially expanding universe expands faster.
Thank you. Thank you, Professor, for such wonderful answer. So, and I also thank you for addressing all these questions with such depth and clarity. While the volume of insightful inquiries reflects the depth of today's discussion, but we must conclude the session to the respect of our schedule. So, on behalf of Bhaktivedanta Institute and all the audience, I would like to once again express our sincere gratitude to you for sharing your insights and wisdom with us today. Your lecture has given us deep insights into science and our understanding of the universe, and we are truly grateful for your time and generosity. Thank you very much,
Thank
Professor.
and
Thank
thank
you.
you very much, and thank you for all interesting questions which you asked.
Thank you.
Goodbye.
Thank you. Bye. Bye.